So since we've gone over all the different elements of a character table, now what we can do is we can actually derive a character table from scratch, given any point group. And as I mentioned in the previous video, there will be an analogous homework assignment where you'll have to derive a character table, and also, guaranteed that's going to be the first question on the first exam. And so, the reason why I make you do this, although it may seem kind of painful, is because you're going to be using character tables throughout the course to solve a wide variety of chemical problems. And so it's really instrumental for you to appreciate and know where the character table comes from. Otherwise, you're just kind of chugging through the motions and solving problems, but not knowing why you're doing what you're doing. So the more you can understand what a character table is, the more that everything you do in this course from here on out will make sense. And so that's why we're going through how to derive a character table. So what we're going to do here is we're going to derive the C2v character table. So I've shown it here. And so how are we going to get there? Well, the first thing we're going to do is we are going to find all the symmetry elements, all the symmetry operations. So we have to think about what does C2v mean, right? Well, we know there's going to be an identity. There's an identity element for any point group. And well, we have a C2v, so that means the primary rotation, principal rotation axis is a C2, so we better have a C2. And do we have any perpendicular C2s? No, that would mean it was a D point group or some highly symmetric point group. So all we have is a C2. You can't really do a C2 twice, because if you do a C2 twice, that's doing two 180-degree rotations twice. That gets you to 360 degrees, and that's back to itself. So C2 twice is the same as identity. So what else do we have? Well, we have that V. So that's telling us we have some mirror planes, or at least one mirror plane. If you think about a molecule in C2v, point group like formaldehyde here, there can show you that there's two mirror planes, right? And so what we're calling these two mirror planes is there's one in the XZ plane and one in the YZ plane. The one in the XZ plane is in the plane of the molecule. This is a planar molecule. Planar molecules always have the mirror plane in the plane, okay? And then we have one that cuts through the carbon and the oxygen. That's the Y. That's the XZ, actually, how I defined it here, this dashed one. And so that's going to take this hydrogen and interconvert it with the other hydrogen and vice versa. And so that's going through this carbon-oxygen double bond. So there's only 4 symmetry elements here. So now we have to identify the classes. And you could go through the rigorous definitions that I told you about in the last video. And if you did that, or just use your intuition might tell you that the two mirror planes would be in the same class. This one's a little tricky. It's easy to derive once you know that they're actually in different classes. So I'm just going to tell you they're in different classes. You could prove that using the mathematically rigorous definition that I went over in the last video. But I'm just going to tell you for this sake, so we don't waste time doing that these aren't separate classes. But know that that would be a tricky one I wouldn't give you on the exam. So they're all in separate classes. So if we have 4 classes, that tells us that we're going to have 4 irreducible representations. That's rule number 4 on the character table. We always have a square. So we're looking to fill in the character tables, the characters in the character table. And for right now, I don't know what the Mulliken symbols are. I don't know what the labels are, so I just call them gamma. These are just generic labels right now. We'll change these gamma 1, gamma 2, gamma 3, gamma 4 to actual Mulliken symbols, but we can't assign the Mulliken symbols until we know what the actual values of the characters are, because it's the values of the characters that we use in our Mulliken symbol assigning rules. Again, go to a previous video to learn, to refresh your memory on assigning Mulliken symbols, but we'll go over it together too here for this specific example. So the first thing to do, once you've figured out the classes, you figure out the symmetry operations, you figure out the classes, you got 4 classes, You got 4 irreducible representations, therefore. First thing to do, put 1s across the board for the first irreducible representation. Every single character table, you can look at all the character tables to prove to yourself this, has what's called the totally symmetrical representation, okay? It's 1s across the board. Just a fundamental property of character tables, okay, and of the symmetry space, that you have to have this type of vector. So that's actually pretty easy. Put 1s across the board. The next thing is to use rule number 1. And rule number 1 stated that the total sum of the squares of the dimensionalities, the first column, had to equal the order, the number of symmetry elements. We have 4, 1 plus 1 plus 1 plus 1, that's our order, 4 symmetry elements. And so this value squared plus this value squared plus this value squared plus this value squared has to equal 4. And the only way to do that is for all the values to be 1. Now note that these values can never be 0 for the dimensionality, and they can never be negative. So if you have positive integers, the only way for the squares of these to equal 4 is for all of them to be 1. 1 squared plus 1 squared plus 1 squared plus 1 squared equals the order, which is 1 plus 1 plus 1 plus 1. Okay, so 4 equals 4. So that gets us a column. And at this point, we can do a few things. You can actually, I call it Sudoku, use Sudoku. If you've ever played the game Sudoku, this is a lot like playing Sudoku. It's kind of trying some things and seeing if it follows the rules, right? The rules of the Sudoku game, which is Sudoku is this number table game. That's one thing you can do, and you can use the different rules to make sure that all the rules are valid. For example, a great one is the orthogonality rule, to look at that. An easier way to start out a lot of times is to think about transforming some vector. So you can use x, you can use y, you can use z, you can use x times y, for example, y times z, or x squared, y squared, you can use y cubed. So you can think about different functions and how they transform. And so x, what we're going to do is we're going to take the x vector. We're just testing. We're testing a mathematical function and seeing if we can get out a irreducible representation from it. And a lot of times you can. Sometimes you won't. You'll get something more complicated. You'll get a combination of irreducible representations. But a lot of times you'll get something simple. So let's try it with x. So if you take x vector, and imagine, so here's your x vector here, and you're going to now do a C2. We already know if you do an x on, an identity on x, you're going to get x back. So if you take an x and you go into 180 degrees, you're doing a C2, you're going to go into negative x. So x went to negative x. That means that the character, and I'm using this Greek symbol chi to mean character, the character for C2 operation for the x vector is going to be -1. So I'm going to write down -1 here. You might be wondering, why am I putting it in the third row, not the second column? It's just because I know the answer ahead of time, so I'm kind of sorting things nicely for us. But if you were doing this, from scratch, you would put it in the second row. It doesn't matter. You can always change the order. The ordering of the rows is totally arbitrary. It doesn't mean anything. So I'm just doing this to match the character table in your book and in the handout online, and kind of the standard way to show it. But it doesn't matter. The ordering of the rows, you could put gamma 3 up here, gamma 2 down there. It doesn't matter. And that's totally arbitrary. Anyway, so x, 180 degrees rotation, C2, that's going to make a -x. So that character is going to be -1. Now let's do a sigma v, so mirror plane reflection xz. So this is a vector, the x vector, and I'm trying to do this dash mirror plane, this xz. Well, that x vector is in the mirror. Anytime you have a vector or any point in a mirror, right, that point's not going to move. It's in the mirror. So x is just going to go to x. And so the character chi of sigma v is going to equal to 1. X went to x. If it goes to the same thing, you put a 1. So I put a 1 there. Now yz. Yz is this other mirror plane. And so that takes any x point and it flips it backwards to -x, right? You're looking in the mirror. You're going to see yourself in the mirror. You're going to see yourself behind the mirror. So you're kind of in the X position. You saw yourself behind the mirror in the negative X position. So that's why we have a -1 here. That was for sigma v prime. So that kind of, in that way, we were able to find another irreducible representation just by translating an X vector. Now we're going to do a Y vector. So Y is here, Y vector. We're going to do C2, 180 degrees. That goes into negative Y, -1. Here I put in gamma 4. Again, that's arbitrary. XZ. Well, that's this dashed one. The mirror is now sideways, so that Y is going to go -Y again, -1 again. And now YZ is this solid mirror plane. Well, YZ contains the Y vector, so we're in the mirror. The Y vector is in the mirror, so it's not going to change it. Y goes to Y, we get a 1. Now the last one, you could try out some different vectors, and you could actually figure this out. But I just do it by Sudokuing it, by inspection here. And you can kind of see that, you have these patterns. 1, -1, 1, -1, 1, -1, -1, 1. So you need, -1s at the back end. That's the only thing that's left. And you can check this, check that this is orthogonal using the rules that we've gone over. So that's why this is really important to know your character table rules. All right, so the last thing we have to do is just assign Mulliken symbols. And so how do we do this? Remember, we first look at the dimensionality. If it's a 1, it's going to be an A or a B. So all these are A's or B's. How do we know if it's an A or a B? Well, is it symmetric with the principal rotation axis? Principal rotation axis is C2. So the ones that are symmetric, those got A's. The ones that are anti-symmetric, -1s, those got B's. How is it a subscript 1 or 2? You look to see if there's a perpendicular C2. There's no perpendicular C2, there's only one C2. That was the principal rotation axis. So then you look for the next mirror plane that pops up, that was sigma V. If it's symmetric with the sigma V, in this case the first sigma V, you're going to give it a subscript 1. So this one is A1 because it's a 1 here, B1 because it's 1 here. If it's -1, you're going to give it a 2. So -1 here, A2, -1 here, B2. Again, look at one of the previous videos and the previous slides for a list of these rules. They're easy to follow, and it's just language type rules. So that's the C2v character table. In the next video, we're going to do a much more complicated one.